Welcome back to Lean Together 2025. Right now we're going to have a presentation by Hannah Fechtner about braid groups in Lean. Take it away, Hannah.
Sure. Give me 1 second. I gotta be able to see my own slides. All right, that'll work. I wanted to talk to you all today about braid groups in Lean. So to me, braids are so interesting because you can understand them as a physical object, a topological object, and an algebraic object. So let me briefly sort of explain what we're talking about. Consider a number of strings glued at the ceiling, twisted around each other, and glued again at the floor. We don't allow something like this. A string cannot loop back on itself. And we consider braids equivalent under either homotopy or ambient isotopy. The notions turn out to be equivalent. There's a nice theorem. The idea is just like physical strings in space. You can move them around. You cannot move one string through another. Again, there's a physical representation. So around 1925, Emil Artin gave a beautiful algebraic presentation for studying braids. You might worry, oh, I have to do parametric equations, I have to do calculus. No, to study them, it's a presented group. The generators are sigma 1 through sigma n minus 1, assuming we have n strands. So the braid on the previous slide had 4 strands, so we'd have sigma 1 through sigma 3. If the generators are far enough apart, if their distance is at least 2, then we have a commutative relation between them. And if they are right next to them, we have what's called the braid relation, which is sigma I is sigma j is sigma j, sigma I, sigma j. So we can also consider a braid group on infinitely many strands. So there we just have infinitely many generators, but the exact same relations. So let's see really quickly how to connect the algebraic with the topological just for some intuition. So when we look at a braid, we can break it down into its crossings. It has overcrossings and undercrossings, and we can name the crossings based on the column they start in. So the first is sigma 1. This overcrosses starting in column 1. And then the next crossing starts in column 3, and the first strand goes under. So we sort of discretize the idea of a braid. So I've just rehashed really quickly so you can see these are our generators, our sigmas, our inverses. The identity in the group is simply the empty braid with no twists. And you can see how if you have sigma I inverse, you could pull that pink strand off of the green to get back to the identity. Similarly, the other way. So it's sort of nice how we can visually verify the algebraic identities. As to the specific relations defining the group, for example, for the braid relation, I'll give the example of sigma 1, sigma 2, sigma 1, let I be 1, j be 2. And when we look at both of these, if you stop for a second and think, you can take that green strand and pull it through the crossing, underneath the pink and over the blue. Similarly, the commutative relation is a little bit easier to visualize. If your generators are far enough apart, you can just sort of swap their heights without messing anything up. Now, I will point out this just shows that the relations hold. It doesn't show that these are the only relations that are needed for the braid group, that these are really the defining relations. The proof of that is outside the scope of this project, but I did want to very quickly give you the intuition, which is you begin with a braid on the left-hand side, and there's a nice proof that it's equivalent under ambient isotopy to a braid with a finite number of straight line segments, and from there you can kind of do some combinatorics of moving the points about. But let's move on to what I'm actually formalizing. So I am following Patrick Dehornoy. He's a French mathematician, sort of the father of modern braid theory. I'm working out of his book. I included the French version because the cover's a little more decorated. But this is relatively recent, 2019, originally published 2021 in English. And to my knowledge, this is the first formalization of braid groups. So knots, a subset of knot theory was formalized in Isabel by Prathamesh in 2015. Unfortunately, that wasn't super helpful for me just because knots, although, very quickly, knots are an embedding of the circle in S3. Really, you can think of it as a closed loop twisted around. They use a different sort of math, a lot of invariants. There are computational packages for Braid. So in MATLAB, in Sage, in Julia. The most useful thing was the current ongoing Coxeter group project because Coxeter groups are defined very similarly to braid groups. They're also a presented group and they have similar relations. So that was enormously helpful. And my definition of braid groups is thanks to them. So I'm going to talk to you about two parts to this project. The first one is simply defining braid groups in Lean. And the second part is my work in progress towards a solution to the word problem in braid groups. So, instead of formalizing directly a braid group, there is a nice generalization of braid groups. Sometimes they're called generalized braid groups, sometimes they're called art and tits groups. They're a presented group where the relations are of the form for generators S and T, ST, STS equals T, ST. They're alternating and they switch with the other one. Both sides must have the same length. And you can't have S equal to T. So you can't have a relation like SS equals TT or something. Or SS equals SSS, I suppose. So in Lean, and I'm going to walk you through this Lean because I really want to, if I hammer home one Lean definition, it's going to be that of the braid group. Um, and so very simply, given two elements A and B and a number, we can make a free group element that's essentially the alternating string of A and B. How I did it, not important, but we're going to use it very soon. Now, the next thing is given any two generators of the group, S and T, we can define a matrix giving the length of the alternating relation between S and T. Necessarily, this matrix has to be symmetric, that is, M of ST must equal M of TS. And then what we're able to do is instead of saying just length for some n, we can look up the value. We say it has length M of ST. And because Lean wants the relations for a presented group to be something equals 1 instead of something equals something else, we just pull that right-hand side over to the left by multiplying by its inverse. So now we can give an art and tits relation on any two generators, which is we just alternate those two generators however long we have to. We look it up, Mij, and then we multiply, we alternate them, but starting with the other generator, and we multiply by the inverse. Okay. Lean's going to require us to have a set of free group elements, not just a relation. So, okay, we take set range. There's a little uncurrying to do to make all the types match. And with that, we just plug this into the presented group infrastructure that already exists. This was probably the most delightful part of my project. I was like, Lean already has this, amazing. So let's now go to the braid group specifically. So, whoop, my animations are a bit off. But so for braids, M of sigma I, sigma j, well, let's look at this first in the center. The length of the relation is 2 if I and j are far apart because sigma I, sigma j should equal sigma j, sigma I. It's commutative. The relation should be of length 3 when I and j are exactly 1 apart. That's the braid relation. And we break from convention in the literature here a bit. If sigma I equals sigma j, we just say there's no relation here. The literature has the length of the relation equal to infinity. That doesn't quite work for formalization. So, oh, this is all out of order. That's okay. So we have braid groups with both infinitely many strands and braid groups with finitely many strands. We implement braid groups over the natural numbers for the infinite case. And the only reason I really have this definition is just to show you it's over natural numbers. The exact how I'm matching it, you can read everything in the light purple up here. And so then we can plug that into the art and tits group. The nice thing, if you look on the right side, is that for the finite case, I'm able to define it in terms of the infinite case because reasoning with fin n is always a mess with hypotheses. So throughout the project, whenever I needed to prove something about a finite braid group, I was generally able to prove it for the infinite group and show a restriction, which has been really nice. Okay, so part 1 complete. On to part 2, which is the word problem. So I think it's well known that the word problem in presented groups is not decidable in general. That came in the 50s with Novikov and Boone independently discovering this. However, we're lucky. For the braid group, it is decidable. There's probably 8 or so algorithms out there. There's a lot of options to figure this out. So Question is how? Which one? Why did I pick the one I picked? So there's art and combing back in the 1920s. Garside, a mathematician from Oxford, had a greedy normal form early in the 60s and it was fleshed out by the 80s. And then Dehornoy, who I'm following, actually came up with two different methods, subword reversing and then handle reduction. I've ordered them in the way I do, from like earliest to latest and slowest to fastest. And yet I'm not picking the very fastest, newest one. I've picked this subword reversing because it's sort of a Goldilocks situation. It's reasonably efficient. It's in polynomial time. But the theory behind it actually is manageable. I feel capable of doing it. Handle reduction requires an ordering on braids that's just a lot more work. It was a good size for this project. And the other nice thing with subword reversing is that it can be extended to a larger class of presented groups called Garside groups. So, once I do this, I can generalize it a bit and get more bang for my buck. I will point out, just as a fun historical note, so like if we look at Art and Combing from 1925, he's got this great diagram. And in the very last page of the paper, he writes, any attempt to carry this out, this normalization procedure, on a living person would only lead to violent protests and discrimination against mathematics. I mean, Lean wouldn't protest violently, but it might overheat my computer. So we're going with subword reversing. Now, the main heart of the algorithm here is taking any arbitrary word and putting it in something called positive negative form. So for readability, I've not written all these sigmas with subscripts and superscripts. I've let sigma 1 be A, sigma 1 inverse be capital A, sigma 2 be B, and sigma 2 inverse be capital B. So the capital letters are the inverses. And the idea is, given any input word, we can somehow move all the inverses to the end while preserving equivalence under the Braid relations. So, for example, we write capital A little a to epsilon, they cancel out. We write capital A little b to little b little a, capital B, capital A. I can leave that to you if you want to puzzle later today to prove that that holds under the Braid relations, that those two sides are equivalent. But the nice thing is you see that the right-hand side is in positive negative form. So as we go through, at each step, you're going to look for the first problem. The first time a positive symbol follows a negative symbol. So I've just picked sort of on line 4, what's the first time? Well, it doesn't happen till the end. And then I've replaced that capital BA with little a, little b, capital B. Equivalent under the Braid relations, and that substring is now in positive negative form. Similarly, I can replace capital B, little b with nothing. So the way the algorithm works is we're trying to determine if two braids are equivalent under the Braid relations. Well, that's the same as saying 1 times the inverse of the other is equivalent to 1. So we just have to decide for an arbitrary word whether or not it's equivalent to 1. So we take in a Braid word W, we reverse it, then we exchange the positive and negative parts and reverse it again. So essentially, we're just making sure everything is sort of sieved through each other. And if the output is 1, then the word's equivalent to 1. And if it's not, it's not. So this is a very simple algorithm to implement. It's just string rewriting. But of course, we're in leans, so you get to show termination and correctness. And this is a bear. So my overall goal is to implement this algorithm. And because it's such a large project, I've broken it down into 3 subparts. So first, I have to define a braid monoid and show its relation to the braid group. That's done in Lean, and we'll talk about that. Next, I have to define an auxiliary structure called grids and relate it to these rewrites, these reversing rewrites. That's in progress because there's a gap in the literature there that I have to fill in. And last step will be to put it all together into the algorithm. So start with the braid monoid. This is a presented monoid with the very same generators, very same relations as the braid group. And I'll just note, if we see it, the equivalence I denote with a plus sign. It looks almost the same. And so the question is, how are these two structures connected? There is a procedure for this. This is a thing done in math, right? We can get the rationals from the integers. It's called localizing. So in grade school, you remember, okay, I've made fractions. How do I multiply them? Well, that should be AC over BD. But I'm going to give you a really quick hand-wavy argument that this uses commutativity. If I put it into a form with inverses, I get A, B inverse, C, D inverse. But I have to group those with positive exponent and those with negative exponent. And so I have to move the C and the B past each other. And then even in the last step, I have to move the D and the B past each other. So this uses commutativity. The normal procedure isn't going to work here to add in inverses and get the group. For example, if you want to see why the braid monoid isn't commutative, here's a very simple. This is sigma 1, sigma 2, and on the right is sigma 2, sigma 1. But you can see, for example, that the pink string starts in the first column and ends in the third, whereas here, the pink string starts in the first column and ends in the second. And because the strands are glued to the floor and ceiling, there's nothing you can do moving the strings around to make those two equivalent. But we're lucky. Øystein Orr in the late 50s, early 60s came up with an alternate route to localize a non-commutative monoid. Actually, he did a ring. And so that actually, I was very happy in the end to find out it was in Lean. Because it lived in ring theory for, historically it was developed as ring theory, and then someone noticed, hey, you can do this for a monoid. I coded it all up myself, but I was saved from having to push it into MATLAB because I found the file, which was great, great day. So while OR localization is in Lean, the specific case where we're localizing by the entire monoid, so we have an inverse for every element, and the fact that we're localizing by a presented monoid, that's a little special. So the theorem I proved is that the OR localization of a presented monoid with generators S and relations R is isomorphic to the presented group with generators S and relations R. So as long as we can OR localize the braid monoid, we can connect it to the braid group. So what do we need? We don't need commutativity. Instead, we need common multiples, which is saying for every A and B that are braid words, there are two other braid words, C and D, such that AC is equivalent to BD. Now note that I'm talking about monoid properties here. So I guess I should have said braid monoid words. So they are equivalent with this plus sign under the positive relation. And you can also talk about left common multiples. You only need one for OR localization. Braids have both. You also need cancellativity, and that's straightforwardly what you think it is. You can cancel on the left, you can cancel on the right. So as part of this theorem, I have to prove both of these. I'm just going to give you a quick intuition for why each one of these is true. So to show common multiples, we consider a structure called the delta braid. It's a half twist on n strands, delta n. If you sort of look, it's totally been flipped over, the colors go in the opposite order. The nice fact about this is we can actually move the strings around so that this half twist can be written with any generator in the first position. So right now, this braid has sigma 1 in the first position. We're reading top to bottom. But I can give you another braid. Maybe I'm going to take this crossing, this green and pink crossing. I'm going to pull it under the blue strand. I'm going to pull it under the purple strand and pull it all the way up. So I've pulled it all the way up. And now I have sigma 3 as the first generator here. That is, you can complete any generator. You can add on to it another braid word to get the delta braid. So logically, if you have something within the right range, you can complete it into the delta braid. The idea for showing common multiples is you're just going to append a whole bunch of delta braids on both sides. It's going to be a whole lot of half twists, and that will be the common multiple of two braids. You'll essentially have a delta braid for each generator in the original. All right, so I'm going to start talking about grids now, even though I said that's part 2, because I found they are ridiculously helpful. So in order to prove cancellativity, we're going to define grids now, and we'll come back to them later again. So let's look. A grid it looks sort of like a Van Kampen diagram, only it's rectangular. It's composed of these cells. And if we look closely, if you follow a path from the top left to the bottom right, that path is equivalent under the braid relations. So for example, if you look in the bottom right, sigma j, sigma I is equivalent to sigma I, sigma j, assuming that the distance between I and j is greater than 1. It's the commutative relation. You can look, okay, Epsilon is the empty string, so that doesn't do anything. This top right is essentially saying sigma I is equivalent to sigma I. Now we can build bigger grids. If we have two cells and one of their sides lines up, we can slide them together. Now we have a bigger grid. I want to show you an even bigger grid. I'm not going to label it. I'm going to go with colors. I can append, so long as the entire side matches. I can't match a partial side, but I can slide this in. I can slide in horizontally to build a bigger grid. And these can get really massive. Drawn out a few too many of them. Now, even as they get massive, one can prove inductively that any path through the grid is equivalent under the Braid relations to any other path through the grid. And these are the Braid monoid relations. So I can take this zigzagging path along the arrows, I could take this blue one, I could go along the border, the other border. If you read off their labels, they will all be equivalent under the Braid relations. And the nice thing is this goes the other way too. If we have two Braid monoid words, A and B, that are equivalent, there's a grid with the left labeled A, the top labeled B, and the other two sides epsilon. This is a big proof. Oh, I wish I had more animations. Okay, so for cancellativity, if we start in the top left, we assume that AB is equivalent to AC, and we want to get down to the bottom right, which is C is equivalent to B. So in the last slide, we've just shown that since they're equivalent, we know we have this grid with AB and AC. And it turns out that grids can be split into smaller subgrids. We can recover the inner structure of a grid if we know that the word on top or the word on the side has length greater than 1. So we can split this out into some grid like so. But we know that the right-hand side has to be the epsilon, so the only thing that can make epsilon is epsilon appended to epsilon. Same thing for the bottom. We have as a theorem that the only grid with equal left and top part has epsilon on the other side, so we can fill those in. And then we have some more theorems about grids saying that if you have epsilon on top and bottom, this arrow is mirrored over to here, similarly for B. So by decomposing this grid and using some lemmas, we're able to get this smaller grid. But remember, every path through a grid is equivalent under the relations. So we get our desired conclusion. So cancellativity actually used common multiples, and it's used this grid structure because the proof is so slick. All right, so that's stage 1 complete. We've gotten OR localization working for the specific case and shown the two conditions that need to hold. So we have a braid monoid, and we know it embeds into the braid group. Okay, now we're going to talk about reversing rewrites in grids. We're going to use these same grids, but we're going to read them in a different direction. And to be totally clear, this is not 100% formalized. I really hope I'm right, but only Lean will tell me with time. So the idea is we're going to allow you to read a grid against the direction of the arrows, and that will allow you to get an inverse. So you can read like so, which would get you A inverse B. You can read like so, which would get you DC inverse, and these are equivalent under the relations. So any path from green to red is equivalent under the braid relations. And note that the bottom right path, that yellow path, would be a reverse word because D is positive and so is C, so DC inverse is positive negative. All right. Now, the other great thing about grids is that given any two side lengths, they exist, and that grid is unique. Well, existence is going to show you that the rewrites terminate, and uniqueness would show you that it's going to be correct. So the proof that we want to show is that these grids line up exactly with rewrites. One direction is easy, and that's proved in Lean. The other direction, knowing that it reverses, you have to construct the grid, is tough. Dehornoy struggled with this. First, he had this idea of using tessellating with cells. That didn't work. He had another idea of completing grids. That didn't quite work. He had another idea here, which is actually very close. He should have gone with this idea. The trouble is, it seems so intuitive. Okay, I'll just build the grid, I'll add the cells in, but it's really hard to formalize. And so he went back and back over his work. Each new paper had a new idea. So I'm pretty darn sure I've come up with a formal way of doing this. It's going to take two new structures, and it's a 3-stage process to get from reversing rewrites to grids. So First off, the rewriting sequence doesn't actually give you enough information. So we need to enhance it to a more detailed version. In a rewrite, you can rewrite sigma I inverse to epsilon, but in a grid, right, and it just totally disappears in your string. In a grid, you still have this cell, and you're going to have to match this bottom arrow up with another cell with an epsilon. You're going to have to match this one up with an epsilon. So we give one that sort of keeps track of the epsilons, the fact that there are now two epsilons there. So that's one step. And then we also need a notion of a partial grid, of a grid under construction. So there's that. Lastly, we must use the grid style rewrites to create the partial grid. And then when the partial grid is done, we can say it's a grid. The first of the three arrows is very much still in progress. The second is about 50% done, but I think I have the representative cases. And the last is done, which is great. So I feel that my definition of partial grid, there's a lot of possible definitions. I don't think it's too strong or too weak because I basically got the arrows on both sides. All right, so overall, just to summarize, part A, localization, done. Part B, connecting grids and reversing, halfway there because I had to make the proof myself, and implementing is future work. In doing this, it was great. I got to beef up the library. I got to do some pull requests for presented monoids. I'm working on a short Lex order on this, made semi-2e systems, which are like non-symmetric presented monoids. But they use a whole different presented monoids are a quotient of a congruence. Semi-2e systems are reflexive transitive closures. And in terms of future work, I did want to really briefly say my hope is to get a Braid widget working in Lean and to use it for educational outreach. I've been doing some outreach in middle schools. And I have the kids using Play-Doh and like appending a braid to its inverse and seeing how it untangles, and it's really great for pre-algebra skills. But the goal is to get a click and drag thing where you can prove in Lean that a braid is equivalent to some other braid just with a series of clicks. All right, well, thank you so much for listening, and that's what I've got.